You can imagine the flow of electricity kind of like the flow of water. Well, there'll be all these little water molecules rushing through a particular point, but in electricity, it would be more like how many electrons are rushing through a particular point. And so we're going to describe current in these units of amps. And I'm going to, sometimes you'll see it in capital A, but I'm going to describe it in like this little curly A, so you can distinguish the difference. But you could think of amps almost as if like the amplification of this particular current in one particular spot. How strong is that current? Is it a high amp or is it a low amp in a particular spot? And we're going to describe the actual units a little bit later, but this is how we can think about electrical current. Now, a very interesting thing about current is that it's always constant along a particular length of wire, no matter what the shape is. So if we have this thing that's all crooked and messed up here, and I draw, let's see, I measure the current right here, this current that went in here is going to be the same current that you'd measure here. Or I can measure it across here in this crazy position right here. And yet all that current is still going to be the same current. I could do it here, and it would still be the same current. So it's kind of weird how this works. But this is just how current works. And even if it splits off over here, let's say if it branches off into this, then we kind of have this I1 over here and an I2 over here. But we'll be able to make this equation that I0 is equal to I1 plus I2. So that's going to literally branch off to be the exact same equal current as that one over there. And when they come together over here, this is pretty important to remember as well, that when they come back together, they also equal the very same thing that they started with. So that's pretty cool. And so we can make the statement that current is constant no matter the shape of this. Now let's really try to define what current is. So I've got this dot right here, and I'm going to draw kind of this line through it. And if we know from voltage in electrical fields, we know that the voltage would be sort of higher on this side, and if we have an arrow pointing this way, then it would be lower on this side because the electrical field points towards lower voltage. And well, it's the same thing for current too. So we would also have current pointing towards lower voltage. And just to make sure that we're very clear, I'm also going to draw a blue arrow here representing the electrical field. And this is also going to be volts over lengths, just in case you have a length of wire here, you want to know the voltage, and you need to know the electrical field in there. It's volts over length. Let's see, volts over meter would be the proper units for that, right? So those two things are pointing in the same direction, and we have this little expression that says I, and that's the representation for currents, equals Q over T. So that would be coulombs on top and seconds on the bottom. All right, so this is just kind of how we can think about how fast and how many particular electrons are going through there, like the speed of it, the strength of it, how many electrons are flowing through that point, at how fast are they going, okay? And so that's kind of what current is. It's interesting. Now the curious thing about it is actually it's in the opposite direction of what the electrons would move, because remember that the electrons move in this direction against the electric field. And so if you know what directions the electrons are moving, you also kind of know what direction the current would be, because it would be the opposite. So these are some clues that will give us like the idea of like what direction is the current going. These are all little clues that we can put together to piece it together. Now let's say the current wasn't going through just a single point, but it was going through, say, an area like this. And you have kind of a whole bunch of charge going through like a thicker area right there. This would be an area. Well, I'm going to point the current in this direction, and then we're going to discuss the current density. And that would be, again, amps, this thing right here, over meters squared, because now there's an area. Now the amps, we've kind of already figured out what that is. It's coulombs over second, so that is amps. And you think of it as like, well, the amplification of how much electrical energy is going through a particular thing, because remember the time, you know, component means like how fast is that current flowing. So you know, the faster it is, the more amps it would be, and the slower it is, then the less amps it would be, that kind of stuff. So that's how we could think of current density, and of course we're going to be expanding it through an area now instead of just a single point, and we're going to be able to say the expression J equals I over A, and this A is now area. Well, that's just a regular area. So we got so many different A's here. We got this A and that A now. There's two different A's we have to keep track of. And then we have I equals the integral of J over dA, because sometimes, you know, when you're having to deal with like constants or variables, those things might switch between having to do the integral, or you can jump through this shortcut. If J is constant, then you can just use the shortcut. But if J is J has a variable in it, then you're gonna probably have to go into integrate it. So, you know, just keep that in mind. We're also going to be discussing the drift velocity, which is how fast the electrons are going through this tube. And we could put that as VD over here. Now they're going to be moving in this direction while the current is in that direction, right? And so we could also say that VD is going to be equal to the change in where they were in the wire. So let's see, we've got a length of wire right here. We've got 1 meter, right? So from 0 to 1 meter of this wire, and how fast did that electron go through? How much time was it that it took? I say delta T, I suppose. So time 1 times 2, and then in position 1 and position 2, how fast did that electron go through there? That would be your drift velocity. Now there's a whole bunch of different equations that we can derive from this drift velocity concept. So let's start with the equation for current again. We can describe that as the number of electrons that are going through this area right here times the drift velocity. So if you calculate the area, calculate the drift velocity, and you know the number of electrons that are going through there, well, then you'll be able to calculate the current. So that's pretty cool. The next one would be something like the current density again. That's going to be amps over area, the double A thing. We're looking at the number of electrons that are going through that at a particular speed. I guess it doesn't, we just don't have the area component on that. So that's interesting. The next thing we can do is the charge, which is the number of electrons times the area times the length. This is just how we can get charge. And then we can also do another one using an integral of I over the time over there. And we'll also describe this N thing as the number divided by the volume. This is kind of like I guess number density, you know, or I guess electron density or charge density or something, but it's really number density here for N, and then you'll sort of put whatever charge is the right charge. It's either going to be positive or negative, but you kind of multiply those things together. This is some different ways that we can represent these things. All right, so now let's discuss resistance and Ohm's law. Now this makes a lot of sense because we're going to say that the resistance is the voltage divided by the current, and that's trying to say, okay, here's the omega symbol, which is going to be equal to the volts over the amps. All right, and if we look at this little diagram over here, let's say we send some voltage over through this wire. All right, now it branches off here, and here's the idea: the branch with the least resistance, the path of least resistance, will get most of the voltage. So most of the current will go through that path. It's going to go right through here. If there's a lot of resistance on this side, it'll go through the path of least resistance. We can kind of say that the current is always going to flow through every path, no matter what, right? But if you start having really strong resistances, the current's going to be so small through that versus the ones that have like zero resistance. If it has zero resistance, all the current's going to flow through there. It's really kind of hard to say this, but we can kind of say that, you know, if the resistance is zero, you know, the current is going to be like basically 99.99%. But it's never going to be like literally 100% through that. It's always going to somewhat branch through the other stuff, always, of course. But, you know, basically the path of least resistance is going to have almost 100% of the current going through there. And now this stuff will work for the things that we're working with in our little classes, which is going to be like resistors and batteries. This will apply, but it won't apply for things that are a little bit more interesting, like diodes, which I don't really even know what those things are, or transistors. You know, all these crazy things that we don't really know what the heck they are yet, right? But a word on these things called semiconductors. Semiconductors, you can kind of you can mix with elements, and that will increase the or lowers the resistance depending on what you want. You can also work with these things called superconductors that become basically have an R of 0 at really low temperature. So yeah, you can kind of do some cool things with those. But basically, we're just going to be working with resistors and batteries, and so we're going to use the Ohm's law for those types of equipment. So if we're trying to calculate resistance of a particular material, we're going to kind of need to know its resistivity. This is kind of just a inherent property of the material, and I'm going to try to represent it with this cursive R. That would be the resistivity symbol for me. Be representing it like this. That would be kind of like a R in Greek, but we know from before that this is supposed to be volume, charge, density. So let's try not to confuse these things. I'll use a cursive R. Now R is supposed to be the R, resistance R, is going to be equal to resistivity times the length divided by the area that we, the length of the material divided by the area, and times the resistivity will give you the resistance. We could also say that resistivity, this thing, is equal to the electrical field divided by current density. Interesting. And this would be represented in ohm meters, like that. This is resistivity. We also have this other thing called conductivity, which I'll represent it with a curly C like that, although just like before, a lot of us will like to represent it like this, but we kind of remember this is supposed to be surface charge density. So I prefer to represent it like that with a little curly C. Now we have conductivity is going to be equal to 1 divided by resistivity. It's literally a flip it around. And this would be equal to J over E, just kind of like that was going to be reciprocal and stuff. And that is going to be conductivity. Now we have power. Now power is kind of like the opposite of resistance, because where resistance was voltage divided by current, power is going to be voltage times the current. So we're trying to figure out how powerful this current is. You just say power equals the voltage times the current, IV. Now we can discuss power that's flowing in an entire circuit. So if we're trying to calculate the whole circuit altogether, we haven't even seen a circuit, but let's consider this like a little circuit right here. Like the sum of the entire power is still going to be, you know, the whole current times the entire voltage. Just consider that. Or we could have just the battery itself, just a little battery, and again we're just going to use the voltage of the battery times the current going through it. So, you know, power is voltage times current. We could represent that over here, volts times amps, and that's going to be equal to watts. All right, and that would be kind of like joules divided by seconds. So joules over seconds is going to be watts. We could also calculate this thing called resistor dissipation, which is kind of like the power that's going through a resistor. So that would sort of, a resistor might release some heat, some thermal energy. And so that's what we might want to calculate, thermal energy being released by the resistor. And so we would say P equals I squared R instead of IV. But if we do know the voltage of the resistor, then we could say V squared over R as well. That's another way that we can calculate the resistor dissipation, the power that's going through a resistor, the thermal energy that's being released, and again, it's going to be joules divided by seconds. So keep that in mind. Now here I've drawn out two little circuits. We got a battery right here, and we got some resistors right here. Now they look pretty similar, but there's a big difference between these two. This one is going to be in series, and this one is going to be in parallel. Now, how can I tell the difference between in series and parallel? Well, this one I can shift. So I could take this resistor and shift it here, and then shift it onto this row, and then they'll be connected onto the same row. And if I can do that, if I could shift it around and put it on the same row, then I'll put them in the series. That's pretty nice. Now this one, I can't do that. I can't just shift this and move it there because there's something blocking it. So I can't really put these two things onto the same wire in any sort of way. And so those two are going to be parallel. All right. So the equations for the parallel resistors are going to be 1 over Req. That's going to be equal to, well, it's the sum of the currents divided by whatever voltage. So the two are going to have the same voltage, all right, but they are going to have different currents. All right, so that's kind of the important thing about parallel. And if you want to be adding these up, remember it's 1 divided by Req. So if you really want to figure out the answer to Req, you actually have to invert your answer to this equation. But 1 divided by 1 over R2 plus that, and plus 1 over R3. So it's actually really easy to add these stuff up. But just make sure to invert your answer. In the series, it's a little even bit easier. Here we're just going to say R equals the sum of all the voltages. So these two now have different voltages, but they will have the same current. So we'll put that here in the bottom, and that means they'll have the same current. And that's because the same current is going to flow through this entire wire. You see, it's got that battery right there. This one may potentially have like 2 different currents flowing. There's 2 different batteries and stuff. So you don't really know what's happening over there. But here, it's just the same battery going through all this. And we try to add this up, then it's just going to be equal to R1 plus R2 plus R3. This one's super easy, just going to add them all up. For this one, remember to invert your answer to find Req because the equation is inverted. So I've drawn a little circuit here, and it's got a couple of batteries at different voltages and a couple of light bulbs. And these are all going to have the same resistances and the same, it's the same light bulb. So, but they're all going to have some resistances. It's the interesting thing about light bulbs. They'll have resistances too. So we're going to try to figure out which direction the current is going to flow based off of the direction of the movement of the electrons. The electrons should be moving away from, well, the strongest voltage, right? So let's look at the strongest voltage, but they should be moving away from the negative. So we're going to go away from the negative or towards the positive. And then we could try to draw the current on the other side. So we'll say, okay, current is going in this direction, opposite direction, right? Current should be going this way. This is IV. And over here, it's going to branch off into 2 different currents. We're going to say I1 and then I2 on this one. I1 and I2. We could even say IV equals I1 plus I2 if we wanted to write an equation. Now this is going to connect over here. And technically, this is supposed to be IV as well, okay? And it should be going this way, IV, because those 2 things are connecting again this way. And it's going to be pushing the current this way, which means that the electrons would be moving this direction, away from the positive, which means the electrons would be moving this way towards the negative, which means the electrons are smashing into each other for some reason, because usually the electrons would be moving this way. If that's the case, if this is a smaller voltage battery and we've got a bigger voltage battery and the current is flowing in the opposite direction, well, the battery is going to be charging itself. So this one is actually charging because the current is flowing the opposite direction into it rather than out of it, right? Okay, so that's kind of crazy. That's what's going on with that battery. We can continue this voltage over here, this current over here, IV, is continuing this direction. It would go this way, and here it would actually branch off into I3 this way. Now, as far as these light bulbs go, they're all going to have the same voltage, and we kind of see that if we look at this. So imagine this current here is breaking off into two equal currents, and then they're just going to go both at the same time, passing through like the same voltage drop. So that's why they would have the same voltage, but look, they kind of have different currents if you think about it that way. But at the same time, if you were to put these two things on the same line, then you would decrease the voltage every time you drop through, because when you pass through one of these resistors, you're decreasing the voltage. So every time you pass through, you're getting like a different voltage. So that's why as you go through and add them up in series, voltage drop, voltage drop, voltage drop, versus over here, you have just the voltage drop is happening at the same exact simultaneous time, and so therefore these things would have the same voltage and two different currents passing through them. Same thing's happening over here. You'll notice these two are in parallel just because they have two different currents. Like, look, they have current 3 and then current 4, so they must be in parallel. Like, they can't be in series if they have this two different currents. So all these are going to be in parallel. The amp meter is like this, and if this has any kind of resistance, then we're going to cause a voltage drop. So therefore, we need to have this to be as close to a resistance of 0 as possible, so we don't cause any kind of disturbance in this. So that's pretty important. Similarly over here, if we were to add another thing over here, which is like this wire, and I stuck this thing over here called a voltmeter. Over here, this is the amp meter. It's trying to read amps. It's trying to read the current, this IV that's going through there. So I don't want the current to be different on the other side. I don't want the voltage to be changed by this resistance. So I want the same current coming out the other side. So 0 resistance. Over here, if I somehow put this voltmeter here, and we're going to take two cases. We'll take the voltmeter having a high resistance and a voltmeter of having a resistance of close to 0. If the voltmeter was really close to 0, then remember the law of least resistance? Then the current is going to start shooting through this voltmeter. That's probably not so good. But we don't really want to mess with this. We want to be able to read the voltage drop across this. And in order for that to happen, we want to make sure that there's no current going through this. We want all the current to go through here and no current to go through there. So if we want that to happen, this thing needs to have a high resistance. So if there is low resistance, this thing is going to shoot through there, which means that if that happens, then these two things are going to start becoming really, really dim, because we could even say that R3, if these light bulbs won't be affected, of course, R3 equals R4 in terms of the brightness over here. These are going to be bright. And these two, if this thing has a low R, let's put this in a low R first. The low R, imagine this is going through there. These two things are going to have very, very low current going through them. So therefore, these things will be kind of like very, very dim. So they're still going to be the same, but very, very dim, almost off, because this thing is going to take all of the current. And so that's why we want this to have a high R, so that way that's not affected. In the case of the high resistance voltmeter, this stuff won't be affected at all, so the brightnesses are all just going to be the same. So R1 equals R2 equals R3 equals R4, so they're all going to be nice and bright. That's the key with these two equipments. Again, they don't want to be affecting the circuit in any way. So you have to set the resistances to be able to do that properly. The last thing we'll discuss is this thing called Kirchhoff Loops. These are kind of like little circles that you can kind of draw. You can draw these anywhere, so let's make sure that these things can go anywhere. Which means I can draw a little Kirchhoff loop here in between those. It's like a circuit. Look, a little circle I could draw there. Or I could draw it in here, along there, or I could draw it in here, or I could do like the whole big thing. Or there's all sorts of different loops that you can make. And this is kind of like a way to calculate like how much voltage and how much current and stuff like that is going through particular loops. So we just want to follow the rules. The first rule is called the loop rule, and that says that the sum of the voltage of all of this is basically when you go through the entire loop, the sum of everything should be equal to 0. That's the sum of all the voltages. You start here with 15, you're going to do minus something, you're going to go, oh, minus 6 this way, and then minus something, and you have 0 at the end, because 15 minus all this gets you to 0 on the other side, so you have 0 to 15. Alright, so it's really important that you add everything up and it equals 0. So for a battery, it kind of makes sense. You're given this 6 voltage, right? But if you wanted to calculate the resistor voltage, then you'd need to use the resistor rule. And that would say that basically you've got this plus IR, and if you follow the current this way, this is the current. If you're following the current this way, then you actually subtract the IR. If you're going against the current, then you're going to add the IR. And what the heck is IR? Well, it's actually delta V. It's the voltage drop across the resistor. So it would be times IR like this. Delta V equals IR. So like this is going to have some kind of delta V, which is going to be R2 times R1, or R2 times I2. That's going to give us the voltage drop across that resistor. If we're following the current this way, you're going to subtract the voltage. And if you go the current against it, so like if your loop is going this way, then, or this way, like I said, your loops can go anywhere. It can go counterclockwise, it can go clockwise. You can just decide whatever way you want to do. But this is the rule that you have to follow in order to make sure that you get this addition properly. The next thing might be the battery rule. I mean, the batteries are pretty simple. They've already given you your voltage here, but there's 2 cases with the batteries. First, we'll write negative epsilon, and this is going to be like this. This is going to be delta V. Well, one thing that's important about these batteries is they don't care about the current at all. So the voltage drop across the battery is always the voltage drop across the battery, no matter what the current is. So it's always 6 on this side, it's always 15 over there. So that's that. But it's possible, let's see, delta V could be equal to epsilon minus this small little internal resistance that could possibly happen if you have a real battery, right? So it's kind of the difference between ideal versus the real. The ideal battery will just be epsilon, that's just the voltage. So you don't have to worry too much if it's just an example problem, for example. But if it's a real battery, if it's in real life, a real battery is going to have a little tiny resistance inside of it, which you'll kind of have to calculate by figuring out what the current is, resistance, subtracting it from the voltage of the battery. And yeah, so that's going to be basically how you calculate the real voltage drop across the batteries. For the final example, let's try to calculate a couple of Kirchhoff loops inside here. We're going to start with the, we're going to make a V loop, and this is going to be the inner loop first. So that would be like this little thing around here, I suppose, right? Just from here to there, follow that and do that. We're going to start here at 15, and we're going to say that epsilon 15, that's how I kind of represent that. We're going to follow this current this way, and we're going with the current across this. So we have to subtract I, which is I1, and then R, which is R1. So that's like this. Then we're going to follow the next one, and over here, well, notice how when we go through here, we're going from positive to negative across that battery. So we're going to subtract 6. It's going to be minus epsilon 6. And then in the next position, we're going to go through here where the amp-meter doesn't have anything, so we're going to skip that. But over here, we're going to follow the current up through resistance 3. We're going to subtract minus I3 R3. And hopefully survive the bombing. But yeah, this whole thing is just going to be equal to 0. So that's pretty cool. That's going to be our loop rule. So when we go over to the other side of this, again, we're going to have the 0. Let's try going on over here to V loop 2, which is going to be the outer loop. This time, I guess we're going to go this way and figure out what's over there. Should be relatively easy. We're going to start with 15 again, and we're going to subtract I2 R2 this time. And then we're going to come through here again, subtracting E6. Hey, if we were going the other way, we could have added all this, by the way. But anyway, we could just keep going. And we're passing through R4 over here. The current is going this way. Again, we're going to have to subtract I4 R4. That equals 0. Now, we can kind of just tell from a couple of equations, that those two things are equal. Look, because the equations state that these two things are basically going to be the same thing. So, you know, we could set those two things kind of like that plus that, and then that equals that plus that. And we can get rid of this stuff if we were to try to manipulate these equations a little bit. You also want to combine these voltage equations with the current equations over here. So in the end, you're going to get like things like, well, IV is equal to I1 plus I2. You're going to combine that and put that in there and try to see what's happening. And then you might even get another one that says that IV is equal to I3 plus I4. So it's just different equations that might help to work together. Remember, you're going to create a set of equations to be able to solve for all this stuff. Anyway, this is basically going to be current. It's pretty complicated.